So we are writing store. That was what we did for our homework assignment with store. And then we're going to expand this for multi-line instructions dealing with, because we already have, we have add I, we have sub I, and then we have load and store. Okay, so we can't write real fancy programs, but we can write programs that put together multiple lines and process stuff like that, right? All right, so we wrote the load last time where we are loading from a memory location. So that is a base address with an offset into a destination register, right? And our base address is stored in a destination register. So I'm going to go ahead and just change my input here so we can kind of trace through this. So this is STUR, and we are storing. So the syntax for that is it flipped, where we give it the memory address first and then? So this is what we're storing, and this is where we're storing it, right? Okay, good. That makes it a lot easier. All right, so we're going to store whatever is in X1 at memory location X2 offset 4, for example. So let's do that. So that looks like a legal instruction we have there. Okay, so our parsing piece should already work as is, correct? We already have our individual little spots. All right, so let's go into instruction. We'll steal our little code here. And this is STUR. All right. But now our destination register, I'm just going to rename these to make a little bit more sense, is really our source register, right? Because it's the source of the value we want to store. So we'll call this guy source register. All right. But that's actually getting read into something called destination name up there. So that just happened to be the naming conventions. If we went back and redid this, we'd probably maybe have a little bit cleaner variable names, but this is adequate for what we're doing right now. So I'll name it better down here so we can keep track of it. So our source register is actually going to be we're going to find the register associated with our destination name. Then we need to get our base register, and this is the same base register we had before. Exact same dude. All right. Then we're going to get that input name. So this is actually our that number, right? And then we get the offset where we take temp and we get a substring from bucket 0 up to its length -1. This cuts off the little square bracket, right? So we don't need to change that. So our offset's right. So we get the base address value by getting the value. Don't have to change anything there. We get the final memory bucket, base address value plus offset. Nothing to change there. Then the thing we actually change is that instead of storing into a register a value, we're storing into memory a value at that register. So we're going to say armap.memory at bucket, final memory bucket. That guy is going to equal source register dot get value. Like that. So the source register is the guy we want to store. The place we're going to store it is our base register value plus offset. And we'll set that place in memory, this guy, equal to the value that's currently in our source register. Okay, so I think that should be it for the homework. Let's go test it. All right, so we're going to have to give some values. So we're going to put something into X1, and we need to put something into X2. So I'll go to my registers, and let's say that we want to store a 5 at memory address. We'll call this guy 30 plus 4, so that'll be putting at bucket 34 in memory. So we'll save that. So we've set up our registers. Now when we execute this, we will store the 5 that we have in X1 at bucket 30 plus 4. So 34. Execute that. Go to memory. I got to do some scrolling. Do less scrolling. There's bucket 34 with a 5 in it. All right. Questions about that? So not too bad. All right. So far, let's just kind of deconstruct this last assignment. Some of you maybe found it easy. Some of you maybe found it challenging. What was challenging about this assignment? Is what we did challenging, or is the fact that we're operating inside of a fairly complex program challenging? That's the more challenging piece, right? We have several moving parts, and you kind of have to figure out where does this go and where does this go and things like that. Okay, so that's kind of the point of why we're doing this, is to get you used to working with, you know, a more intimidating code base than you might be used to working with in class. I think I mentioned that last time. All right, so if you found, I mean, now that you've seen this, I presume that changing this one line doesn't seem like it was all that bad, right? Fairly simple assignment when you consider what actually had to be done. But getting to the point of, this is where we put this code, this is our, we copy the stuff for our load, rewrite it a little bit. You know, I happen to just change this variable's name because I think it made some sense to change the name. But all in all, we didn't do a whole lot, but getting to the point of knowing where to put that small change was the more difficult part. Okay. All right, so now we have several things in our arsenal in terms of instructions that we can execute. We have stores, load, subtract, adds, sub, well, is subtract and add immediates, and then normal add and subtracts. All right, so these are all things that we know how to do. Now, typically, our programs are not one line long. Typically, we're going to have programs where we have multiple lines of things, where maybe we store a couple of values. Well, maybe we load some stuff into registers. We now actually, hold on. Is there an instruction in? So I definitely want to give us this. Do we have an instruction to just load an immediate value into a register? Like if I want to say move into X0 the number 5. That's got to exist. Where's my list of instructions? So that'd be a helpful guide to write real quick. I don't think I can get to this, right? In x86, it's called move. Do we have a similar thing here? This is still loading from memory, loading from memory. Okay, yeah, it's this move. So what's the difference between move wide with 0 and move wide with keep? Okay, so this move Z, they don't have a normal move instruction. So we have two different things here. And actually, this is beneficial. I think I mentioned this way back when we hadn't looked at this, where in Intel-based assembly, there's a high and a low side of a register. So you might have a 16-bit register and maybe called AX. And you can get at the first half of it, or you can get at the second half of it individually as two 8-bit, and treat that 16-bit register as two 8-bit registers. So with that in mind here, they have a version of MoveZ, well, a version of move. So treat these both as moves, where we can move an immediate value into an individual register. This one pads it out with zeros. So this one is the safe one, where we say, it doesn't matter what's currently in the register. I'm going to go ahead and zero out that register and then move my value into it. Or you can think of it as, I'm going to move my value into it, my binary value, and then pad it with zeros, everything else. Hence, overwriting what used to be there. Okay, because in an actual computer, our registers are holding binary values. Okay, so MoveZ permanently overwrites the entire contents of the register with the new value. Whereas MoveK only overwrites the bits of the register that are being overwritten. So for example, let me show you this. Because this is kind of a fun one. Oh, that's not this class. We're 325. All right, so we'll look at this as MoveZ versus MoveK. So I'm going to write it as just a bunch of bits. So let's say we initially have I'm just going to treat it as a 16-bit register for now, just so I don't have to write too many more zeros. All right, so we have a 16-bit register, and let's say the default value is all zeros. That's what we've been doing. We've been zeroing out our registers to begin with. All right, so let's say that I add the, and just for the sake of argument here, just put a little split the first half and the second half of our register, just so we can visually see it. So if I do a move, it doesn't matter if I do a move Z or a move K initially. So let's say I do a move Z. We'll say this guy is X0. That's what this register is. So if I say a move Z into X0, the value 5, let's say. So a binary 5 is what? 1, 0, 1. Okay. So I'm going to go ahead and copy this whole thing for a minute. So it'll look like that. Okay. Now, if I do a, let's see, 1s, 2s, 4s, 8s, 16s, 32s, 64s, 128s, 256, 512, 768. So we'll say, if I do a move Z, X0, 768, like this, what'll happen to this guy is it will look like that. Okay, if I did a move Z. So this is the 512 bit, this is the 256 bit. Add them together, that's 768. Okay, so this is the number 768 across all this. That's if I do a move Z. Make sense? But if I instead would have done a move K, it would have looked like that. So I'm going to keep the other bits. So that allows me to deal with the high and the low side of the register if I wanted to by purposely loading into the low half. This is the 1s, 2s, 4s, 8s, 16s, 32s, 64s, 128. So the values between 0 and 255. And then the values between 256 and 32,767. All right. I think so. All right. So I can deal with both halves. That might be the reason for using move Z versus move K, is whether or not you want to override the entire register and use the whole thing for a value, or whether you want to move two different values into a register, meaning two separate things. And this almost gets back to programming when we talk about our primitive types, where we have all those different ways of storing whole numbers. So bytes, shorts, ints, and longs. Why do we need so many different ways? Well, memory used to be expensive, blah, blah, blah. Well, we kind of have that problem in spades here with hardware registers. First of all, hardware registers are expensive anyways. Still, they don't hold a lot of space, and pretty much they're the reason why processors cost so much. Okay, that, and then, you know, when you look, if you price the difference between like server processors and normal processors, so if you look at like the Intel Xeon processors versus the normal Intel, you know, i7, whatever, what's the big thing that changes between Xeons and the consumer processors? It's more of an IT question. Besides price. Okay, so you're looking at a 3 gigahertz i7 processor versus a 3 gigahertz equivalent i7 Xeon. Okay, and the Xeon is 4 times the price. Is it just because it says the word Xeon on it? It's like the computer equivalent of the Nike swoosh. Why is it 4 times the price? Anybody know what the differentiating factor typically is? That is possible. It might have more cores. I would say typically you can probably get a consumer processor with the same number of cores, but that's not a wrong answer. It very likely might have more cores, but let's pretend like that's not the answer I was looking for. It's not a wrong answer. Server processors typically will have more cores, but they don't have to. But every server processor will have more of this than the similar consumer processor. Which memory? It's what are our choices for memories? Okay, well, processors don't have RAM on them. So what are our choices of memories on a processor?
L1, L2, L3.
L1, L2, L3, and then the registers. Okay. It's possible you might run into a server processor that actually does have a larger architecture, so maybe there are more registers, but let's not call that common. What you'll really see the difference as being is the L1, L2, L3 cache. Significant difference. And what you'll see is you might see a normal i7 might have 256K of L1 cache, something like that. And you might see that an expensive Xeon processor has 4 megabytes of L1 cache. Okay, we don't think of megabytes as being all that big, but when you're comparing it to 256 kilobytes, that's a lot. And we've already had a discussion that the closer you get to the processor, the actual the core in the center, the more expensive that RAM is, the more expensive the memory is. So typically, if you go and price two processors that look the same on almost every aspect, look at the L1, L2, L3 cache, and that's where you'll see that will scale with the dollar signs associated with the processor. All right. So how does that help us? How is L1, L2, L3 cache actually used? Like, when does that benefit us? This probably would have been from one of the I'm in India readings. You have plenty of time to memorize the book from that. So a lot of times it's and we're about to kind of sort of emulate it in our little interpreter thing here. But to increase the speed at which the next instruction gets into the CPU, we kind of preload that instruction into cache. Kind of makes some sense because it's quicker to move from L1 cache into a register than it is to move from system memory into a register. Make sense? So our loads and stores, they go from registers to system RAM. And even though in human world, system RAM is still really fast, a load and a store in processor world is a relatively slow function. It's kind of the equivalent of the human world of file I/O. So if we have a computer program that reads in from a file and writes out to a file, that is a relatively slow thing, even by human standards when we're writing a program, especially if your source for the hard drive is a mechanical drive as opposed to a solid state. So that's a thing where you feel it. Okay, so if you have a 1 megabyte file, let's say, that you're reading in when you start your program, you'll actually feel the little pause in your program while it reads the data in from that file, especially from a mechanical hard drive, okay, because it's slow to read in from a file on a mechanical hard drive. The equivalent of that at the processor's level is reading from RAM into a register, presuming it will fit, is relatively slow compared to reading from like cache into a register. That make some sense? All right, so L1, L2, L3 cache, they are nice staging areas for data that we will need soon. Okay, where L3 is the one that's shared between the multiple cores in a CPU. So if we have a single CPU that has like quad cores, 4 cores, things that might need to be shared between those individual cores, we throw into L3 cache. Okay, because that's kind of almost like a singleton. Okay, if we're connecting this to more programming stuff. So we have a single object that all the cores want to have access to. So any one of them can hit the L3 cache, right? Because of how it's set up. Whereas L1, L2 cache are per core. All right. So keep in mind that's even more of what drives that cost, especially in the situation where Alexis is likely right most of the time, where a server processor probably does have more cores than the kind of equivalent class consumer processor. Because now if you have significantly larger memory or even just a little bit larger memory for L1, L2 cache, that's on a per core basis. So if you're looking at a 4-core processor versus a 12-core processor, and you have 4 megabytes of L1 cache, let's say, that's per 12 core, per each core out of 12. And since the closer you get to the processor, the more expensive memory becomes. That's a lot of memory you're paying for, hence the reason the processors are so much more expensive. Make sense? All right. So the operating system itself is what's going to utilize those L1, L2, L3 caches for speeding up the delivery mechanism for getting an instruction, an assembly instruction to the processor. Otherwise, we have to rely on getting it from system RAM, which 16 weeks ago we thought was fast. Now we're realizing isn't as fast as it seemed because there's faster memory. Okay, so if you want your computer to really chug along, we want to keep that CPU fed as close to 100% of the time as possible. Okay, and why is that more important in a server type setup where there's likely more L1, L2 cache, that kind of thing? It's probably because there's also likely more cores. So that exaggerates this, exacerbates this. Yeah, that's a better word. That's a fun word, exacerbates. And you also typically have multiple users using the system at once. So you're far more likely to be utilizing those multiple cores because you have multiple users all stressing the system at the same time, running multiple versions of system programs. Okay, so makes everything faster because you have more people sharing, let's call it the same resources, and now you want to give enough support there to allow that to still be fast for them. Okay, and if you and then the alternative to that might be, how many of you have ever used a virtual machine on your computer before? So whether if you're on a Mac, you use Parallels or VMware Fusion or something like that, or if you're on or there's a virtual PC, it's a free one, right? A couple other ones, but if you're on a Mac and you want to run Windows on the Mac side, you run a virtual machine. It's convenient for starting point, right? What's the downside? It's slow. What's the other downside?
Lots of memory usage.
Well, that's part of the reason why it's slow. So, but if you're running Windows inside the Mac, let's say, so your Mac OS is booted up, and then you're running Windows in there as an application, as a virtual machine, the Windows is slow, but your Mac OS is also slower. Why? Because it's having to share the resources between two operating systems. And when that virtual machine loads, regardless of whether you use those operating systems or not, or those resources, it grabs the resources. So if you create your virtual machine to have 4 gigs of RAM, okay, and you have 8 gigs of RAM in your computer, your virtual machine, the second it launches, will steal half the system memory of your Mac, whether it ever uses it or not. So now your Mac only has 4 gigabytes to work with. Okay. Same thing if you with your hard drive. If you are launching a virtual machine and you say, I'm going to give this guy 120 gigabytes of hard drive. What it's going to do is it's actually going to put a kind of a special file on your hard drive that's 120 gigabytes big. Now, some of the newer virtual machines, they will let that scale. So they'll start off in a smaller kind of like, let's wait until you grow to this, and then we'll stretch it. Okay, that way you just don't take up tons and tons of hard drive space. But you probably felt it the most with mechanical hard drives. If you're on a solid state drive now, if you have the same system set up today as you did previously when you were running the same virtual machine, and the only difference is you have a solid state drive today versus a mechanical hard drive, you probably notice a pretty substantial increase in performance just because of the hard drive. It's probably the one aspect of your computer that makes the biggest difference in perceived performance from a human being's perspective. And that gets back to what we said a few minutes ago, that file I/O humans feel. We don't necessarily notice the microseconds that it takes to load something from L2 cache versus L1 cache, right? It's not going to change our life. It adds up over billions of instructions per minute or something, but we're not going to notice that much. But we will notice the difference between a solid state and a mechanical hard drive because that's slow. All right. So if you're ever looking to upgrade an older computer and you're on a budget, swap out the mechanical hard drive for a solid state drive first. 100% of the time. Unless you're just dealing with a ridiculously low amount of RAM. Like you have 64K of RAM or something like that in it, then maybe you have bigger problems. Because at that point, you don't have a mechanical hard drive. You have I don't know, like a gerbil or something in there with like a little stencil or something like that. I don't know. I mean, it might be a chipmunk. It doesn't have to be a gerbil. I don't know. What was it talking about? Oh, yeah, chipmunks and gerbils. All right, so we understand the difference between move Z and move K? Makes sense? It would be situational when we might use something like that, but as a developer, if you were trying to be cautious about the amount of memory you're using, or maybe more realistic in today's world, we wanted to preserve, we're certainly dealing with a limited number of registers. Okay, maybe we don't necessarily care that a register is 32 bits versus 64 bits. Maybe that's not really a limiting factor for us, but the fact that we only have 32 registers, that might be a limiting factor for a more complex program. So in that case, if you need to store smaller values, you might choose to kind of double up and allow a X0 to actually hold 2 different values in it by dealing with the high and the low side of it. And then if you really want to play around with that, technically, if you're storing small enough values, you could store more than 2, right? You just have to deal with the right bit space for where those values are being stored. Everything's kind of a map offset. So if you want to store the number 5, but in the first 4 bits, you need to scale it up to be something that's large enough for the first 4 bits that actually ends with a 101. So it would be bit 30, 31, 32, 33, 34. So that would be 2 to the 30th plus 2 to the 29th, no, 2 to the 30th plus 2 to the 28th. That's the decimal value you would store to store the number 5 in the far left nibble of a register. That makes some sense, or is that just gone? All right, let me draw that out. Squeezing lots of data into a register. All right, so before I go into this, do we at least understand why you might want to do this? We have a limited number of registers, and if we're storing small values, we might choose to store 2 or more small values inside of one register rather than waste a lot of space inside of a register and store 2 small values across 2 registers. Make sense? In a complicated program, that preserving those extra registers could be a big deal. All right, and if the values are small enough, we could technically store more than 2 values. So, for example, if we say, what is it, x0 that's the name of a register. All right, so if we decide we're storing really small values, right? In 4 bits, we can store 0 to 15, right? This is kind of our hexadecimal space. So let's just say we wanted to store 4 small numbers in our register. Realistically, you probably only would ever store 2 numbers in a register, but just from this is how it would work perspective to exaggerate it. If I wanted to store a 5 in x0, I can say I want to move, actually I could say move z or move k, doesn't matter for this first one, x0 comma 5, and then I would have, this would produce a x0 of this, just like we did before. Okay. Now, if I then wanted to get 101 here on the far left, the far left nibble. Okay. So in my mind, I'm saying actually let's store a 6. So let's store 110, just so it's a different number than the 5. So I actually, if I want to store a move k x0 6 like that, but I want my intended output. So what I'd love for my output to look like is that. That's what I want my output to look like. It won't look like that right now. If I just say move k x0 6, what I'll be left with is that with zeros over here. All right, because it's just going to overwrite that the first part of those buckets, leaving the ones where they were, because I'm keeping those extra bits. So if I want to get this to look like this, I'm going to have to store not a 6 here, but a scalar that will ultimately set these 2 bits. All right, so this is the 256, 512, 1024, 2048. This is 4096, 8092. Yeah, 8092. And then 16, blah, blah. So this is 2 to the 30th plus 2 to the 29th. So that's this value. So I'd actually move that value into x0, keeping the bits, which would load this in there. Go ahead.
So I've got a bit of a explanation on these pulled up, and it looks like you can kind of scale the immediate, similar to the store and load functions.
You can accomplish the same thing that I'm doing here by, instead of just putting this giant value here, I can push it bits.
Right, you can do left and right shifts.
Okay, yep. So with that in mind, your value in here would be what it would be, like a 2 left shifted 30?
Something like that.
No, actually, you would start with a 6 and then left shift. You would say move K X 0. Your scalar would be 6 left shift 30.
Yeah.
That should shift your 1 1 0 over to the left. So, but not worrying about that too much. This is the outcome of that. If you took the number 6 and you left shifted it 30 times, you are taking that value and putting all these zeros in front of it to get you to this point. Actually, it would be left shifted 29 times to get you there, producing this number, which is this number. Make sense? So if I didn't want to do the shift thing, or I didn't understand the shift thing, or I didn't know it existed, then I could just say, well, to play with this left 4 bits here, I just have to store a really, really, really big number. And this is actually a data representation for the number 6 stored in the far left 4 bits of a 32-bit number. But I have to know that I did that. Okay, because if I want to treat this guy as 4 different numbers here, where the center ones right now are zeros, and I want to extract this piece from here, what I would need to do is, when I dealt with these bits, I'd have to only deal with the far left bits, and then specifically say, turn those back into a number, because that's the number 6, not this scary number. Make sense? That gives you kind of the ability to store multiple values inside of one register, if it made sense for you. All right. In our world, we might say that it would make sense just from the perspective of we don't want to run out of registers in a complicated program. What's the other way that we avoid running out of registers? Go ahead.
Storage.
Yeah, loads and stores. Don't have room for it in a register? Toss it into RAM. Bring it back into a register when you need it soon. Right? So that then puts our architectural limitation on only being able to work with, at one time, the number of registers that exist. Probably -2, because you're probably going to have a 0 register and a flag register. But ballparky, the number of registers that exist. So if you only have 32 registers and you need to make us, do some math that involves more than 32 registers, you're going to have to do it in pieces. Do part of the math, then store stuff, load things back in, and do the rest of the math. Because you're only capable of working with those registers up to your 32 or something like that. All right, so that's when you might decide you want to do a cleaner job here. Realistically, in today's world, well, first of all, very rarely in today's world are we actually writing assembly, except in here, which is fun. Okay, but at least we're writing high-level code that then turns into assembly. In the real world, what is generating our assembly for us? Who's in charge of generating our assembly? Yeah, compilers. Okay, so we're very reliant on that power tool, the compiler, to go and generate our assembly code for us. So we just write the fancy schmancy high-level code. We don't think about registers or where you're going to store crap. Who cares? Deal with it. This is beneath me, right? That's why we're very reliant on the quality of our compilers. But hopefully you see that a very good compiler might take, for example, if you have a variable that's defined as a byte, which is only an 8-bit number, it might decide to go ahead and store that only in 8 bits rather than waste 16 or 32 bits to store that value. Make sense? Okay. Oh, and by the way, in the last few minutes, I've been treating this verbally as a 32-bit number. It's actually only a 16-bit number, right? So this is actually not even accurate. This would be an overflow. So this is 24. This is the 2 to the 26 plus 2 to the 27. That's what this number actually should be. 2 to the 26 plus 2 to the 27. Did I get a value? Big money. Well, whatever. It's that value. Equally, it's a big value that I don't want to read, right? But it's actually that value, because this is not the 31st and 30th place and the 29th place. This is the 14th plus 13th. Is that what I did? Yeah, it's actually this value. I think I was saying one thing, but actually wrote something else. That's what that is. 2 to the 14th plus 2 to the 13th is what you'd need to move into X0 to set only these bits with a keep. If you set it as 0, it'll just zero out everything and then store the number. All right, that makes some sense? Okay, so let's go ahead and let's write. We could write a move K. We've written a lot of the logic to let us do a move K because we actually have the ability to store binary numbers. But for the sake of time, and because we want to get multiple things written in here over the next couple of days, we're just going to write a move Z because we've been storing things just as decimal. So look, if you're going to change it to a 13 from a 7, you're overwriting the whole thing. A 7 became a 13 now. You haven't preserved any of it. All right, so we're going to take away that flexibility of us being able to write to parts of our registers in our program, even though we get how we could. We're just choosing to store our stuff in decimal right now, as opposed to storing our stuff in binary, where we'd have granular control over the bits. We've lost that granular control by making it convenient for humans to use decimal, but we'll keep it convenient for now. So I think this program's complex enough at this point. We're happy with the level of complexity. It's just trivial enough. All right, so we're going to go ahead and let's write a move Z. Then we'll leave it called move Z just to remind us that it's a special dealie. All right, so do it. Oh. Yeah, here we go. So we'll do a move Z, X3, comma 7, something like that. And this allows us to move an immediate value into a register, zeroing out the rest of the register. All right, so this guy should be fairly easy to write. So let's go into our instruction. Now, move Z, go back out here for a second. When we had add X0, X1, X2, something like that, we had 3 different inputs, right? When we had our load and store, even though we only had 2 inputs from a human perspective, we were able to treat it as if we had 3 because we had the extra comma in the middle of our stores and loads, right? We would like do a load X0, comma, bracket, X1, comma, 4. Something like that. So we were able to treat that as if it was 3 inputs, even though when a human glanced at it, they could say, oh, there's only 2 inputs. There's the source or the destination, depending on which one we're doing, and then the memory information. Okay, but we were able to do a split on the commas. But in this case, we're not going to have that. In this case, we actually only have 2 pieces of information. That makes sense? So we are going to have to treat this guy a little differently. One thing we could do is, if we wanted to make this a little bit more generic, what we could do is we could create a list of inputs. If we can assume our inputs are always separated by commas, we can create a list of inputs, which we're currently doing. We're just pre-splitting them out, right? So if I go into my instruction here, when we create an instruction, we pass it the string here. This is where we're breaking the pieces apart. All right, so I'm going ahead and peeling off my magic trick. So that part, we're still good. That's always going to look the same no matter what instruction we're working with. Get everything up to the first space. Didn't I trim that last time? Oh, I trim it when we read it in, right? So when we hit our execute button, here's my get text. Well, I don't trim it there. So it's not trim there. It's not trim. Oh, I trim the whole instruction right here. Yeah, so that takes everything off of both ends. All right, so we're good. All right, so my magic trick, that guy's not going to change. That every instruction in ARM has a magic trick followed by stuff. Okay, so we're good there. So now we have our stuff piece of this. So we have this variable called the rest. And the rest gives us a lot of information, because this is just going to say, here's a string that is everything but that. That's everything but our magic trick. Then we go ahead and get the parts of this guy. So now parts actually has everything in it that we need. Whether we have 2 components like we are looking at now, or we have 30 inputs, 30 parameters, if you will. Parts has everything. But we're actually storing parts as a local variable here and then splitting it out into destination, input. Well, we're creating our input names here. So we're always treating this first guy as destination, even though we've seen with a store that it's actually the source, not the destination. So we're kind of giving it maybe bad names, something like that. So we could give ourselves this parts array here, give it to us globally, so that we have a collection of the comma delimited pieces, and then on a per instruction basis, go and manipulate those pieces how we needed to, rather than making some pre-decisions in here about what they might be called. That makes sense? We originally wrote this with the idea that we were writing adds and subtracts, which all look the same, which these 3 things make perfect sense. All right, but now we're actually going to write it as, we're going to take our parts. So I'm going to create a private variable up here. We'll say private string array. And we're actually already putting it into input names. I think I might end up dumping input names. I'm just going to create a string up here called, let's call this guy parameters. So then in here, I'm going to say this dot parameters is equal to that stuff all split up. Okay. I'm going to dump my little linked list of stuff here. And I'll dump it here. So by doing that, it's going to point out all the places I'm currently relying on that, right? All right, so at this point, what I have is I have a string array called parameters that has everything divided up by commas that's following my magic trick. And that should be suitable for any assembly instruction. Okay, so when we come down here, I need to delete these because I don't have a destination name anymore either. Destination actually lives in bucket 0 of parameters. All right, so this dot destination name is actually, can I refactor this guy? Doesn't seem like it should be a rename. Is that a change signature? Yeah, find and replace would actually probably work. But I like using refactoring because that's a software engineering term. So let's do, there we go. So that did it. I just did refactoring, I renamed it, and anywhere where it said the thing before, it now says parameters at bucket 0. Input names, get 0 should now be the parameters at bucket 1. So I'll right click, refactor, rename. This is going to be, have to do it in pieces like this. I don't like that. It won't let me do the whole thing at once. And I think this might be a find and replace thing. I think you are right. Does this give me the ability to replace? Nope. There we go. Oh. So I'll search for this guy. And I'll say this dot parameters at bucket 1 is what I'm going to replace that with, right? So get 0 is going to be bucket 1. And then I will search for this guy. And that'll be replaced with bucket 2. Okay, I think we're still functional now. All right, so instead of having 2 separate groups where I had my destination register and then I had my inputs, now I just have a single string array called the parameters, which has all of the parameters that are being fed into this particular magic trick. Now I knew that for my loads and stores, these guys down here, I had to be a little bit wily with those guys just because I knew they had some square brackets and stuff like that in there, but that's okay. I was able to, this is what it looks like, I'm going to deal with it. Okay, so now I can go ahead and do an else if this dot magic trick dot equals ignore case, and we're going to look for this guy to be move Z. All right, so now for move Z, we're going to need a destination register. So we'll go ahead and steal that guy from there. So that's where we're going to put it, right? Okay. Then we need to know the value that we're putting there. So we're going to get parameters at bucket 1 and convert it to an int and then store it. So this is going to be destination. What did I do? Destination register dot set value equal to integer dot parse int this dot parameters at bucket 1. Like that. So that's a move Z. Where do I want to put it? What do I want to put there? This is what I want to put there. I want to put the integer version of my second parameter. Where am I going to put it? I'm going to set the value of my destination register that I found using AR map along with parameters at bucket 0. All right. So if this works, move Z x37. After I execute this, I should be able to go to registers and see that x3 has a 7 in it. Ruh-roh. Something died. Whatever the error is, I did it on purpose.
We're going to adjust it to number format.
Oh, because it's got a space. Yeah. See, I did do it on purpose. Where am I at? Instructions. Yeah, this guy right here, technically, the current way we're writing it is space 7. It's the string space followed by a 7. So I need to trim that. Realistically, it's probably a good idea to always trim. Oh, what? Even with the trim?
Like, saying adoption.
We'll make sure this guy is an array of strings. This parameters at bucket 1 should be a string that I'm pulling out of there. Strings have a instance method called trim. And there's my x3 is 7. Okay. Now, I have the ability to move stuff into places. So now I can sort of kind of write a program that has more stuff in it. Did you get your error cleared up?
Yep.
Okay. So let me get rid of this. What did I do? Hit the X. Okay. So as we currently have this written, this guy allows us to write one line. Okay, but we probably want to be able to write more than one line of code in there to test it. So we want to change the way this guy might work. So let's see. Does this let me have multiple lines? All right, so what I'm going to do, here's my instruction edit text. I'm going to go into text up here. And we have a multi-line text. I'm going to drag that here. The input type is text multi-line. So I'm going to delete that now. Text Where's my text multiline? This is funny. I'm actually pretending like I can read this. There we go. Oh, no, it's up here. All right, so now this guy can handle multiple lines. So I'm actually going to go ahead and stretch it out a little bit to give me some more space in here. Now, just because of where the keyboard will pop up, I'm actually going to take this execute button. I'm going to bring this to the top. And then I'm going to take my registers here and my memory. I'm going to bring that to the top. That way our code's kind of below. Because keep in mind, our keyboard is going to kind of slide up here. Okay, so you know, since the keyboard is going to slide up in this space, we want to have this guy, I don't know, positioned reasonably. So I just have it at 200 DPI right now. We can always change that. I'm going to do layout weight stuff, so I'm actually going to set this guy to a layout weight of 0.1, this guy to a layout weight of 0.1, and then this guy to a layout weight of 0.3, something like that. So that should be, I'm at 50% then. And then what I'll do is I will take another vertical linear layout and toss it down here. And I'll give this guy a layout of 0.5 and have his height set to none. Or do I have to set it to wrap content? That guy has a 0.5. This guy has a 0.3. This guy has a 0.1. This guy has a 0.1. So this should be, oh, do I need to do the guys inside here? No. So this layout weight, that allows you to separate it along the screen. So this should be, this top thing should be 10%. Why is this not closing here though? Oh, whatever. There's that. There's this guy, so I'm going to give that smaller, 0.2. We'll just call that reasonable. You can mess with it to see how you want it to look. I just mostly wanted to get my way of typing down here and then everything else below it because the keyboard is going to be blocking us. Yeah, so there's my keyboard in there, so I can presumably type stuff. All right, but this stuff is, I can scroll within there to get to all my different text, but then I have to hide that guy if I want the keyboard to go away. So I could make it a little smaller, but I can still get to my registers and all that jazz. All right, so I'm going to change the gravity of this guy to being top and left. That way we're kind of writing it in a normal file. All right, so we should be able to now do things like I might have to type it somewhere else and copy it there unless I can do \ns. Okay, that's technically working. Oh, my add I is currently wrong anyways. So I'll move into X3 of 7. I'll add an immediate, storing an X1, the value of X3 and a 5. Then I'll move into an X4 of 13. Then I'll add X0, X3, X4. And then maybe do it STUR, X0, comma, X1 offset 5. Something like that. Oh, and I need to put a \n before that. All right, something like that. So for Monday, or Tuesday rather, you should have your execute button process a whole list of instructions, any number of instructions that is in this text box, ultimately having your registers in your memory in its final state as the result of those guys. That makes sense? So I will commit this. So you'll have the up to the minute version of this guy. So I'll say move Z implemented, commit and push. All right, so you already have inside of instruction the ability to handle any one of these individual commands. So now you need to process through a list of commands stored in here and execute each one in order such that your registers in your memory will finally show the outcome. Questions about what I'm asking you to do? Going once, going twice. I will see everybody on Tuesday.